Welcome back to our video series on using SPSS to perform inferential statistical analyses. This time we'll be addressing assignment 3, which covers the one-way and two-way analysis of variance, or ANOVA. We'll begin with the simplest case for ANOVA, the one-way between subjects ANOVA. This analysis is used when a researcher wishes to compare means for a single continuous dependent variable between two or more independent groups of participants. Before we jump into the details of the one-way ANOVA, let's take a minute to just look back on the ways that we've already learned how to compare means between groups. Recall that we've used the t-test to compare dependent variable means between two specific groups. The one-sample t-test is used to compare the mean of one group to some standard or to a norm. You'll recall in the Clark and Stoner article, the authors used a one-sample t-test to compare the spelling scores of Brailling students to a national norm. In the independent samples t-test, we compared the means of two independent groups to one another. And finally, in the dependent samples t-test, we compared the means of one group on two different occasions, such as with a pre-test, post-test type study. However, if you'd like to compare the means between more than two groups, you'll need to use a different type of analysis. That's where ANOVA comes in. In a one-way ANOVA, there may be two or more categorical groups evaluated on the means of a single dependent variable. This is the topic of the current video and of Chapter 8 in the Yaki text. In a two-way ANOVA, there are two independent grouping variables, such as gender and race ethnicity, and a single continuous dependent variable. This type of analysis will be covered in Chapter 9 of the Yaki text. Recall that the null hypothesis for the independent samples t-test states that there's no difference in the means of the two groups being compared. As we'll see, the independent samples t-test is very similar to the one-way ANOVA. The null hypothesis for a one-way ANOVA evaluates whether there are differences in means between two or more groups. The null hypothesis in this case is that no differences exist between any number of groups. By convention, we use K to represent the total number of groups subjected to analysis. We can think of the ANOVA as being the big brother to the t-test. With the t-test, you can compare the means of only two groups, but with ANOVA, you can compare the means of more than two groups. In fact, the outcomes of the t-test are identical to a one-way ANOVA using two groups. You'll confirm this relationship as part of your assignment for Chapter 8. So let's take a closer look at the one-way between subjects ANOVA. Suppose we have a case where we want to compare the means of four different groups. For example, the test performance of African American, Asian, Hispanic, and white students. The null hypothesis is that all means are the same between all four groups. The analysis in this case is asking the question if there's a difference between the means for all the possible pairwise combinations of groups. So the primary analysis in a one-way ANOVA is an omnibus test to see if there's a difference in means between any two of the groups. If the results of the analysis lead you to reject the null hypothesis, all you'll really know is that some difference exists someplace between at least two of the groups. The omnibus test does not tell you where the differences lie. So, if your null hypothesis is rejected, you'll want to run some additional tests to determine where there are differences in means between the groups. There are several such post hoc tests that may be run in this case. Post hoc tests are run after the main ANOVA and indicate which groups are significantly different from each other. When reporting results of statistical analyses, it's customary to include certain information in the write-up of the results. Recall that in writing up the results of the t-test, it's appropriate to report the value of the t-statistic, including the degrees of freedom, as well as the effect size expressed as Cohen's d. The test statistic in ANOVA is the f-statistic. When reporting the value of the f-statistic, it's required that the 2 degrees of freedom are also included. The degrees of freedom are based on the number of groups, or K, and the total sample size, N. The effect size in an ANOVA is expressed as eta square. Eta square is calculated as the sum of squares between groups divided by the total sum of squares. As we'll see in a moment, these two values are produced by SPSS as part of the ANOVA analysis, but it's up to the researcher to actually perform the calculations. Eta square can be interpreted as the percentage of variance in the dependent variable that's explained by the categorical independent variable, or the individual's group membership. To use the example mentioned earlier, eta square indicates the percentage of variance in test scores that may be attributed to a student's race ethnicity subgroup. This image represents the ANOVA table produced by SPSS in a one-way ANOVA analysis. In this case, the null hypothesis that all the means are equal should be rejected, based on the p-value of 0.021 reported in the last column, labeled as sig. In order to calculate the effect size, eta square, you'll need the sum of squares between groups and the sum of squares total from the table. To calculate this effect size from this ANOVA, you divide the value for the sum of squares between groups by the value for the sum of squares total. In this case, it's 91.487 divided by 367.867, which is 0.249. This means that 24.9% of the variance in the dependent variable can be explained by the independent variable or the group membership. The value for eta square should be reported in the text or in an APA formatted ANOVA table as shown here. Finally, let's take a look at the three assumptions of the ANOVA. First and foremost, each observation must be independent of all other observations. This means that individual participants can be classified in only one group. In addition, participants should not be influenced by one another or subjected to similar conditions that may affect the outcome variable. The second assumption is that the dependent variable is normally distributed for each of the groups in the analysis. Recall that in class we discussed several ways to determine whether a dataset is normally distributed. Finally, it's assumed that the variances for the data for each of the groups are equivalent. Standard ANOVA analysis includes a Levene's test, which may be used to verify that variances are similar. Well, that does it for the background information on the one-way ANOVA. In the next segment, we'll take a look at the sample analysis in SPSS.